Hey, hello. Happy Sunday. It's Sunday for me. I don't know. Oh, hi. Henry says hi. You want to say hi, Hen? Say hi. Yeah, she says hi. Okay, I'm gonna jump right into it. This week we are doing cryosphere. Um, which has a really close place in my heart. I love the cryosphere. Uh, the cryosphere effectively pertains to all of the ice on Earth's surface. This includes glaciers and snow caps, and ice sheets. So we're going to talk about the differences of those and why this matters. So I made this an entire module in and of itself because it is a sphere of Earth's system, which we've been talking about. But also, it's a super, super important sphere, and climate change is really affecting this particular system, and vice versa. This system is also affecting climate change. So I think it's really important. I also did my master's thesis pertaining to the last glacial maximum and the cryosphere, and how that affected paleoclimate. So this I took from my environmental science class. Oh my God, there's cat hair everywhere. I'm so sorry. Um, I took from my environmental science class. We also talk about water and water availability. And I wanted to show a really nice image. I really like this image about the distribution of Earth's water. So on the far left, we have the entire distribution of Earth's water on our planet. 96.5% of our water on Earth is in our oceans. So it's salt water, right? We had a whole module on this, right? We had a whole hydrosphere module on this. Of all of Earth's water, only 2.5% of that is fresh water. So not very much. And of this fresh water, 68.6% of that fresh water is stored in our glaciers and our ice caps. So that's a really important number. Most of our fresh water is frozen. Where's it going to go? So glad you asked. That's what we're going to talk about. So glaciers form when repeated annual snowfall produces deep layers of snow that are not completely melted in the summer. It's a flowing body of ice that flows under its own weight by the force of gravity. We're going to talk about what that means. This isn't, well, it is true for all ice sheets. They all move very differently. The dynamics of the ice sheets are very complicated and very nuanced, but they all move based on their weight, and their mass. And where's that ice sheet going? Is it going down a topographic hill slope? Um, is it on a flat space? In which case, how does that move? We'll talk about that. If you've ever seen the movie Frozen 2, which is by far the superior Frozen movie, maybe that's an unpopular opinion. But Elsa goes off on this self-discovery journey to find out where she got her magic ice powers from. And she ends up in this northern island that is a glacier. And she's like, oh my God, it's a river of flowing ice, which is accurate. That's what glaciers are, is essentially a river of flowing ice. And they move very slow, relative to real rivers. But they have the same, they're water, right? They're very similar in properties to regular rivers. So we'll talk about that. Perennial snow is the term for snow accumulation that lasts all year. And there are three general types of glaciers. They each have their own subcategories of glaciers, but we're not going to dive too hard into those. But we are going to talk alpine glaciers, ice sheets, and ice caps. And I'm actually going to start with ice sheets, maybe, because they're the biggest. So ice sheets are the size of continents. They're fucking massive. They can cover millions of square kilometers of land. And they also might be really, really thick. So there's two currently. The two biggest ice sheets in the world are Greenland and Antarctica. And remember, these are over the continent. So these are land-based ice sheets. We do have polar ice sheets that are over water, which you'll see in lab this week. But in terms of ice sheets, we focus primarily on the ones that sit over a landmass. And the biggest ones are Greenland and Antarctica. The Greenland ice sheet is the largest ice mass in the northern hemisphere, with an extensive surface area of over 2 million square miles and an average thickness of up to 1 mile. So this is topography. It's really hard to see, and I do apologize for that. But this is one of the images in your textbook, so I think you can click on it. and see. But the average thickness of this sheet is about 1 mile. And it goes up to 3,205 meters in its thickest location. So ice sheets are really interesting because they sit on land. And this, I mean, yes, this land has topographic features of hills and valleys and slopes and all that. Because it covers so much area, the way that these sheets move is they actually move outward. So this, imagine like, what's a good analogy? Imagine you set like a ball of goo, I guess, or slime. You roll up a ball of slime and you put it on a surface counter. That goo is gonna like force its way outward, but in every direction, equally in every direction. The same is kind of said about these ice sheets over land, is most of the accumulation of this snow takes place around here. And over time, it's sort of spreading out, getting thinner around the edges, but that ice sheet is moving out directionally in every direction, pretty equally. So you can see the topography here is relatively equal in every direction. So they like smoosh down. It's pretty cool. Pretty cool. And the same process is for Antarctica. And they have Antarctica here. Here's a cross section of Antarctica. So here's the land. And then this is how thick that Antarctic ice sheet is. Does it give me directions? South to north. So here's the South Pole. So we're going south to north here. It covers almost the entire Antarctic continent. The thickest parts of the Antarctic sheet are about 2.5 miles thick. That's crazy. I do want to point out, towards the end of this slide show, I talk about the last glacial maximum because that was my specialty. So of course I'm going to talk about it some more. And over Bellingham, over Whatcom County, during the last glacial period, which was about 20,000 years ago, or I guess the last glacial maximum was about 20,000 years ago, an ice sheet sat over Whatcom County in Bellingham that was about 2 miles thick. It was a lot of fucking ice. Very heavy, right? It's ice. I don't know if you've ever tried to pick up a block of ice. It's not light. Imagine 2 miles of that over this area. And it's so heavy, in fact, it's one of the reasons this whole area has been scoured out the way that it's been scoured out. But it's so heavy, in fact, that the land under it actually starts to sink into the mantle just a little bit. Because of this huge amount of mass over it. And once that ice sheet melts, or once it melted, our land actually started to rise back up again very slowly. It's still rising. I mean, the ice sheet over our area was 20,000 years ago, but it's still rising. This is called isostatic rebound. And I'll talk about it a little bit more, not next module, but the module after, when I talk about the local geology. So ice caps are smaller versions of ice sheets. They cover less than 50,000 kilometers squared, usually cover higher elevations, and may cover tops of mountains. So these are a little bit different than alpine glaciers in the sense that, yes, they still move, but a lot of these are confined to like basins or like bowl-shaped topography. So they don't have a lot of space to move. They're not flowing like ice. Some of these are in landforms called cirques. Some of them are in basins, and they cap tops of mountains. And they still move, they still flow based on the accumulation of the snow, but they don't move the same way that alpine glaciers move. So alpine glaciers, these are the famous glaciers that we see on most of our mountains. This is Baker. She has lots of alpine glaciers. They form on mountain sides, and because they are part of this steep slope, they move. They move downward through valleys. And a lot of times, the reasons that the mountains have these valleys are because they've been carved out by these glaciers over time. They can create or deepen valleys by pushing dirt, soil, and other materials out of their way. And they're found in every single continent except Australia. New Zealand, which I don't know. Maybe I'm just not geographically inclined here, but I'm pretty sure New Zealand is part of Australia. Maybe not. But New Zealand has glaciers. But the actual mainland continent of Australia has no glaciers. Africa has glaciers. So Mount Kilimanjaro, which is the volcano at the start of like the Lion King that you see. It's a really famous volcano in Tanzania. It has alpine glaciers. So all of the continents have glaciers except Australia. Fun fact. So how do these glaciers form? There's a lot of physics and a lot of math that actually goes into this. And I had to take like 3 different classes that just talked about glacier formation. And it's so fucking nuanced and it's so dynamic that I'm just going to brush the surface, the top surface of glacial formation. But essentially, what happens is you have snow that falls as part of these glaciers form packages. And that starts as I'm pointing at the screen as if you can see it. And that starts as a glacier, or sorry, that starts as a snowflake. And they're beautiful and they're stunning and individual, right? And over time, the snowflake gets compressed and it becomes granular, it becomes more circular. This is like a blurry picture of a snowflake, but imagine it becomes more circular over time, right? And then you have more compression that occurs, more layers of snow are added to that snowflake, and that comes what's called a firn. They're small, tiny, compressed ice particles. All of that air has been pushed out, all of the water has been pushed out. It's just compact ice. And then over time, you get that glacier ice. So you go from snowflake to granular to firn to glacial ice. And here's a really cool image of a moraine, ice cored moraine, which do I want to dive into? I will. We'll talk about a moraine here shortly. So glacier ice, you can kind of see the layers here. Each one of these layers is a different year of snowfall. And so it'll fall, it'll compress. And then you'll have more snow over that, compressing all of this material over time. So each one of these layers is a different year of snowfall. And we as scientists, we take ice cores from Antarctica, from Greenland. We take these ice cores and they can give us information that are hundreds of thousands of years in the past. Actually, hold on one second. I want to show it. I think it's cool. Okay, I had to add this because I think it's really fascinating. It's a little blurry and I do apologize. So this is an ice core. We drill these in Antarctica and Greenland. And so my undergrad was at Oregon State University. We have a huge core repository there. So what that means is we store sediment cores, and we also have a huge freezer that stores Antarctic and Greenland ice cores, which is really, really cool. And you have to have like special permission to even enter the ice core one because it's so much data that if you walk in there and they start to melt, you fucked up everything. It's very intense. I've never even been in the ice core one. I worked with sediment cores, so I got to see those, but not ice cores. So this is an ice core. I think this one was from Antarctica, if I'm not mistaken. And you can see very vaguely, and I do apologize, if you have the PowerPoint open while you're going through this, you can see these like darkish bands and these lighter bands. The dark ones indicate like a winter season or a really cold season where there wasn't a lot of melt. And then these sort of cloudier ones represent summer seasons. There's a little bit of melt within this, so there's some mixing. That's generally the overview of colder ice is a little bit clearer and warmer ice is a little less clear, I guess. I'm no ice core expert, but I wanted to show this one because then we have this really dark band of material here. And you're like, well, what the heck is that? That's not ice. It's not ice. This is probably, and it didn't say on the website I was looking at, but I'm 99% sure that this is volcanic ash. So in the past, where we have had huge, massive volcanic eruptions that cover the globe, it's also covering ice sheets, it's not just covering land. So this was likely a volcanic deposition from either Mount Mazama, which was its crater lake. I'm trying to think of other massive ones it could have been in the past. It might have been Vesuvius. I don't think Vesuvius went that far. My guess is Mount Mazama, but there are a couple other eruptions it could have been. Regardless, it's likely 99% sure a volcanic eruption, which is really cool. So we also get that sort of that history as part of this story that this ice core is telling. And we take these cores because the chemistry of these cores will tell us a lot about past climates and past events that happened globally. So glaciers as a system, this is where a lot of physics takes into play. And I took this was where my 3 classes came into play. I learned all about this. This is kind of a more complicated diagram, but all you need to know is at the top of this glacier is where we accumulate that ice, that material, right? And there's generally a consistent amount of accumulation over the year. Obviously, winter we get higher amounts of accumulation and summer we get less. But any type of precipitation, we're going to have that accumulation. And so this glacier accumulates and it flows. And as it flows, we might lose some of that snow. It's called ablation, to wind, to avalanches, sublimation. If you remember, sublimation is where ice goes from ice to gas, which we learned in hydrosphere. I'm pretty sure I taught that in hydrosphere. Yeah, I did. And at the end, we might have meltwater, which if it's reaching a water source like the ocean, it's going to melt into the water. It might not reach an ocean source. It might reach just an elevation in which the temperature can no longer contain that ice, so it melts. And we'll get river systems, we'll get streams, glacial outwash. And underneath the ice sheet, we also see what's called internal and basal melt. So there are a couple different types of glaciers. And in this area, which is what I will focus on, we have what are called temperate glaciers. So they're warm-based glaciers. We have melt at the base of these glaciers because of the temperature, not just because of temperature, but temperature plays a huge role in that. Also because of the mass. If you go to your freezer right now and you get out an ice cube and you push that ice cube on the desk as you go, it leaves behind a layer of water. And that has to do with the pressure that you are putting on this ice. The pressure between the bottom of the ice and the surface that you're running it across, the pressure gets so high that it melts the water. So that's what's happening with glaciers too. So glaciers flow in this area because of two reasons, because of the temperature, but also because of the pressure and the gravity, I should say. I apologize. So three reasons. Gravity, pressure, and the temperature. Did I say all the right things? As it's moving down this slope. So there's water at the base, and that water essentially lubricates that glacier to make it move. That's where I was getting at. So the water at the base is a lubricant. And in a perfect system, we have the same amount of accumulation as we do ablation. So we have the same amount of snow coming into our glacial system as we have leaving the glacial system. Now, obviously, that's not going to be true for our current glacier systems. We have more ablation right now than we do accumulation. Although, do I want to say this? Your homework assignment is going to ask you to write about one of the local Cascade volcanoes. Not right, but you're going to do a PowerPoint presentation for one of the local Cascade volcanoes. And one of them, I'm not going to say which one, but one of them has the most snow accumulation of all the Cascades in the entire Cascade range. But because of its location, it gets the most amount of snow, but because of its location, it also loses more than it is gaining over the year. And it's really fascinating, actually, that we get the most precipitation and it gets the most snowfall, but because of the temperature and because of its location elevation-wise, it loses way more. So it doesn't keep that snow. It does not maintain it as part of its glacial system. Hopefully, if you pick it, that's great. If not, I'll bring it back in the last module. I'll talk about it again in the last module. So how do glaciers move? I have this really cool video. And if you can't see it as part of this Zoom, because I know I'm recording on Zoom, I have also posted the link. I would go to 54 seconds in because it's like let's talk about this first. You don't have to watch that. This is a time lapse of how glaciers move. So they move very slowly. I don't even know what glacier this is. I think it says it in the video, but so it moves like a river. You can see that it's moving down this valley like a river, just at a very slow pace, at a very slow rate. Had to be time lapsed. Oh, I don't know what that is for you to see it. Some lady talking. I just think okay, I don't care about that. We'll go back here. So the movement of this is very fluid. It's very malleable. Now it's not water, so it's more brittle than water, but it is still relatively ductile. It's moving as if it would in a river valley. Back to my PowerPoint. So why do we care about the cryosphere? So glad you asked. So there are a couple reasons, and I'm sorry, Henry. I had to adjust my legs. My leg's cramping. If you remember in hydrosphere, I showed you this map. It was also on your midterm. This is your global surface salinity map. What this shows is average salinity in surface water. And we're seeing that most of that salinity is here in the Atlantic because it's confined by these continents. But I wanted to point out that Greenland has less, around Greenland, here's Greenland here, has less salinity than the rest of the Atlantic. And that's because this ice sheet is melting. And it's okay that it's melting annually. We want this to happen because as it melts, it's pouring in cold water into this system. Antarctica is doing that too, but not at the same rate that Greenland is. So why is this important? Because of the ocean conveyor belt. So Greenland is melting this ice sheet into the ocean, and that is causing the deep water, the deep bottom water, the near the Greenland area, which is helping that convection process. So our ocean current, our conveyor belt, is effectively started because of where it is with Greenland. So this ice sheet melting annually is a super important component to our modern climate. If we lose this ice sheet and we no longer have bottom water forming, that's going to make the currents, the water currents in our ocean, get super fucked up. And I actually don't know in what capacity they're going to get fucked up, but it's not going to be good. So when I say that the cryosphere is affected by our climate, right? It's being melted because our climate is changing and our overall temperature is getting warmer. Our cryosphere also affects our climate. So if we lose this ice sheet entirely, which we're on a trajectory right now, let me tell you where it might happen. I don't think we'll fully lose it in our lifetimes, but in the next few hundred years, we will see. Well, we won't, we'll be dead, or humans will see. But if this melts fully and no longer is producing cold water to form this deep circulation, that's going to change the ocean currents, which is going to change, if you remember, El Nino and La Nina. Those are, oh, no, wait, you don't, because that's in climate. No, I did talk about it. Whoo, you guys, I'm mixing up my environmental science and my geology, and I do apologize. We did talk about La Nina and El Nino and atmosphere. And those are both affected by ocean currents as well as atmospheric circulation, right? There's two different components that drive El Nino and La Nina. And if we start to change one of these factors, which would be the global conveyor belt, it's going to change a lot about our climate. So climate affects our cryosphere also affects our climate. It's this positive feedback loop that we're stuck in. And we'll talk about feedback loops next week in climate change. So if we lose all of the Greenland ice sheet, and this is dramatic, but it could happen, we're going to see a change in the sea level. And what that's going to do is it's going to affect our coastal cities. And I think, oh gosh, I should have memorized, or I should have looked up the stat before I just spat it out. I'm just going to spit it out. It's like 70 or 80% of human population live near coastal areas because it's accessible for food, it's accessible for water, it's accessible for climate, blah, blah, blah. People love the coastal areas. And right now, from 1880 until 2020, this is the average rise, I guess annual rise, of our sea level in millimeters. Millimeters are small, but just in the last math, oh God, 120 years, our sea level has risen almost 250 millimeters. That's a big deal. Okay, and then I have this other YouTube video. Again, it's located here, so if you can't see it perfectly on here, you're also going to look at something really similar for your lab this week. But this is what the Earth would look like if all of the ice melted, not just Greenland, but if all of the ice melted. So Oops, I'll just let it run. If it's not perfect on Zoom, I do apologize. But you can see it's showing you these cities that are going to be pretty dramatically affected if sea level rises due to ice melt, just ice melt. Okay, I want the United States, though. That's where I highly recommend watching this whole video. It's really fascinating. I just want to get to the US. There's Mexico. Here we go. Portland's fucked. Seattle's fucked. Florida is super fucked. Like, whew, bye, Florida. Florida's just gone. Louisiana's pretty fucked. Anything on the East Coast is pretty screwed. This is if all of the ice melts. So on the lab this week, we're just going to look at Greenland, not Greenland and Antarctica. And that's important because, so here's what it looks like in just the US. And that's important because we're in our lifetime, and probably for the next few centuries at least, we're not going to lose all of the ice. But we're going to lose a significant amount of that ice, at least in our lifetime. Okay, let me go back. Escape. I recommend watching this whole video. It's really interesting. You won't need to watch it for the lab. We have another unit we'll use for that topic, which I'll talk about in my lab video. Oh, oops. But my not so fun fact about this is if all of Greenland's ice sheet melts, sea level will rise approximately 7 meters. And then if all Antarctica's ice sheet melts, the sea level would rise approximately 60 meters. 7 meters alone is terrifying. That's a lot. Greenland is by far the most at risk for melting faster than Antarctica is. They're both melting. And they're both melting at a high rate. But Greenland is by far melting much faster. Come on up. Well, don't yell at me. Do you want to come up or not? You have space. There you go. So hold on. I'm trying to transition this topic really nicely so you're not just like, bam, new topic. We talked about what's going to happen with ice sheets melting. But I want to talk about the fact that this has happened in our past multiple times, hundreds of thousands of times. Climate changes naturally. And this is an okay process. It's a known process. And we know this because of something called the Milankovitch cycles. Oof, I've been saying that word for years and I still can't get it down. And that has to do with Earth's orbit, its tilt, and its effect of its wobblingness, how much it wobbles. All of these factors, these three factors, contribute to changing climate pretty regularly. So precession is the wobble that Earth moves at. I don't know how else to describe it. The change of Earth's wobble changes about every 26,000 years. It's important. It is not the most important component of our climate and what I'm about to talk about. Obliquity is the angle at which our Earth is tilted. So this is our magnetic pole. And right now it's not 24.5, it's 23.5 right now. We're at 23.5 degrees tilt off axis. So we're not perfectly up and down, right? We're tilted. Hopefully we are familiar with this. I talked about it before when I brought down my globe and I showed you we're at a tilt, right? But the most important one in regards to climate change, at least, I don't know, maybe I'll have some climate scientists fight me on this. But the most important one that I think is most important is eccentricity. And this is the orbit around the sun. Sometimes we orbit in more of a spherical shape, but sometimes we have more of an elliptical shape. And what this means is that in points of Earth's history, our Earth has orbited a little bit further away from the sun, which allows it to cool a lot faster. And this change occurs about every 100,000 years. And the reason I think it's the most important is because we have had glacial interglacial cycles that occur approximately every 100,000 years with this eccentricity. Hi. So here's today. This is just the last 450,000 years. I have a map or I have a diagram that goes back several million, but it's really hard to read because the squiggles get really small, right? So this is just the last 450,000 years. And in the last 450,000 years, we've had 4 glacial periods. So this is the average temperature, annual temperature. And 4 times in Earth's history, just in the last 450,000 years, we've hit below this 20 degrees. Now you see it's not perfect. Sometimes we see these little bloops above that, but overall we see these glacial periods approximately every 100,000 years. Our last period ended about 20,000 years ago, but it lasted about 1,000 years. So our interglacials effectively mean that we had no glaciers. And all of that water that we saw that was on top of the land, or it was changing the coastlines of the land, the shorelines. That's happened before. What we'll learn next week is it's because this is a fight that anti-climate change or climate change deniers have. They're like, well, this has happened before. We've had warm periods. They're right. We absolutely have. But the rate at which we are changing our global temperature is significantly faster than we've ever seen historically. So we've had this glacial period. We're in an interglacial period right now, but we're in the midst of it. So obviously we still have ice sheets, the Greenland ice sheet and the Antarctic ice sheet. They're not gone entirely. So we're in like the middle of it, changing from glacial to interglacial. But what we're considered in an interglacial because the glacial maximum has hit and it has receded. So we're dealing with a time of, okay, well, we're melting. And yes, we're supposed to be melting as part of the Melanchthon cycles. Again, we're melting a lot faster than the globe has ever seen before. We have never, in the history of glacial and interglacials, we have never seen glaciers melt as fast as they are melting now. That's all I'm saying. So the last glacial maximum, again, this is what I did my thesis on. This was one of my figures. Okay, let me just read the words over here. So there were 2 massive ice sheets over the North American continent during the last glacial period. And the last glacial period, let me just go back maybe, lasted about 115,000 years ago to about 20,000 years ago. So again, it lasted about 100,000 years, this whole period that we consider the glacial period. There was the Laurentide ice sheet and the Cordilleran ice sheet. So over in the right here, we see this massive ice sheet that covered North and South, sorry, just North America. Over the eastern part was the Laurentide ice sheet, and I ignore that. It's important, but But I focused in on the Cordilleran ice sheet. So here's the Cordilleran ice sheet, and here's the maximum extent of that Cordilleran ice sheet, and it covered Washington, Idaho, and Montana. And the reason we split it into 2 ice sheets was because they, I know, because they behaved differently. And we have different data sets for each. They're along this mountain range. So the Rockies are sort of over here. The Idahoan mountains are also over here. And because of this, we split it into 2 ice sheets where they behave differently. So as these ice sheets retreated, they also formed a series of lakes within the continent. I also want to make a point to say, it didn't just advance all the way down and then retreat, and that was the glacial period. We have evidence that this ice sheet advanced and retreated, advanced, retreated, advanced, retreated, and then maybe when I say retreated too, I also want to make it clear, this ice sheet didn't physically move back north. So hold on, let me stop sharing real quick. So imagine this ice sheet, right? It's massive. It's moving from the north to the south. This is important. So it does move from the poles. So this ice sheet is moving from the north to the south. As it's colder, as those temperatures are colder, as we have ice and snow falling at the top of this ice sheet, it's spreading out. Remember how I said with the Greenland ice sheet, it just sort of spreads in all directions. The same thing was happening at this time. All of that ice is moving southward. When it recedes, it doesn't physically move back north. It just melts. So this ice sheet, we call it receding, but it's just melting. But it does melt from the southernmost boundary further north, right? Because those are the thinnest areas as well. So, oh, go away. Let me share again. Share. Let me find my Greenland one. So with Greenland here, we had this ice forming, this ice accumulating in the center spot, and then it's pushing this ice out and it's getting thinner around the edges. And because these are thinner areas, this is going to melt faster and reveal that landmass much faster than it will in the center. And this is where I would ask, does that make sense to my class? And they'd either be like, no, I don't get it. Or they'd say, yes, I understand. But obviously this is not a super interactive class. So hopefully that's making sense. So all the snow is accumulating up north. It's pushing this ice down. This is important for the sort of the later parts of my slides, which we're almost to. So it's pushing this ice down. Oops. And I studied the Puget Lobe here. So we're going to look more at the Puget Lobe here in a second. And then when we talk about local geology, local, et cetera stuff, I'm going to talk about the Missoula floods. And I'm going to talk more about this flooding and the lakes here because they're really cool. And I wanted to talk about them now, but I was like, it doesn't really pertain to cryosphere, but it will pertain to the local area. So we'll talk about more of that. So if you've heard about the Missoula floods, they're really fucking fascinating. And it had to do with the last glacial period. I also want to point out that because we had this massive fucking ice sheet that sat over the entire North American continent, or at least the northern part of the North American continent, all of this was fresh water that was stored on this continent. So here is a really cool depiction of where the shoreline was approximately 20,000 years ago, based on topography and elevation. So the sea level was approximately 125 meters lower than it is now because all of that water was stored in these ice sheets. So Florida was huge at one point. Good job, Florida. All of the East Coast had way more shoreline over here. And then over time, as this ice sheet melted, our shoreline became higher and higher and further west. And we also have sedimentological records. So we have geologic record that also depicts this. And I won't dive into that because that's also super complicated. But just know we have a lot of evidence that shows where our shoreline was as these glaciers were melting, which is so cool. It's so awesome. And the East Coast definitely had a much more variable shoreline than we do now over here. So I didn't show this side. I couldn't find a great one for the West Coast. But just know, even on the West Coast where we were at, the shoreline was a lot further down. So here is the reconstruction, essentially, of how this ice sheet melted over time. This was part of my thesis, too. So here's the Puget Lobe where we were at. As it melted and receded, again, it's not moving south, or sorry, it's not moving north, but it was melting and it was all of this glacial water was constrained by the Olympic Mountains and the Cascade Mountains. So only outlet was modern-day Chehalis River. So we were at one point also completely submerged in glacial water. Once the ice sheet actually reached the Strait of Juan de Fuca here, all of this glacial lake, we called it Glacial Lake Russell, drained immediately out of the Strait of Juan de Fuca, like super fucking fast. And again, we're going to talk about this in 2 modules when we talk about local stuff. This is the same process that occurred with the Missoula floods. But the reason I brought this up now is because the reason, too, that this was such an important thing to note is understanding that these ice sheets are changing. I wrote the dates. Is also going to be really important with seeing how the environment is changing, how ecosystems are changing. So when we lost this glacial landmass, when we lost this ice sheet, our environment and our ecosystems also changed, and they changed really dramatically. So this was my thesis exposed. It didn't expose, we kind of had this idea, but we got more evidence to sort of back up this theory, this hypothesis. So we hypothesized as part of my thesis that when this ice sheet was over the Puget Sound, the only plants that were really able to thrive were shrubs and ferns, forbs, because there was so much ice there that these annual plants could come back when it would get warmer in the summer. But trees really didn't start to show up until that ice sheet retreated, which is going to change the entire ecosystem of the area. It's going to change the environment. It's going to change the climate. It's going to change what animals, what humans are going to be able to live in this area. So that's the point of why is the cryosphere so important? It's going to change the fucking ecosystems, and that's going to also alter a lot of what we know right now. Glacial landforms. This is actually a really great poster, and it's terrible as a PowerPoint presentation because you can't see shit. So I'm going to show you the evidence that is glacial landforms. There's this really cool program, which I recommend you look into. You don't have to as part of this. Ooh, maybe I will do it for local. Ah, that's a great idea. I might bring this in for local homework. TBD, but if not, this is called the Washington Geology Portal. It's free. I love it. I use it almost every day of my life. And it shows really cool geologic features. And one of the things that it shows, this coloration, sorry, it's going to go in and out here for a second. This coloration is gray. It's called LiDAR. And LiDAR is a satellite image technology. Hold on, I gotta just turn off my space heater. Henry left me anyways. It's a satellite imagery that effectively strips away all vegetation, which is awesome for geologists. This allows geologists to really see the geologic landforms of the area. So like here are our Cascades. We can see topographically our Olympics, our Cascades, but let's zoom in to the Salish Sea. So we are, oh God. This is embarrassing. I should know that. Oh, here's Bellingham. Yay. So here's Bellingham. I am, oh no, down here somewhere. Oh yeah, because here's Orcus. Oh, here's oh, oopsies, that's Anacortes. Ha! Look at me go. Okay. Here is Salish Sea. And let's see if I can find a really good. Yeah, I guess they're better down south. So further south, in the actual Puget Sound. So I guess let me exit out of this. Let me zoom out entirely. Because boop boop. Okay. I'm zoomed out because this entire waterway here from east of the Vancouver Island all the way through Washington and the Strait, this is what we consider the Salish Sea. All of these waterways are the Salish Sea. The Strait of Juan de Fuca is here, so this is where we get currents from the ocean and then they leave the ocean. But we consider just this area as completely confined by these land masses. Not confined because they're in and out of the Salish Sea. This is the Puget Sound. So I say, oh, this is the Puget Sound. Technically, that's not right. Up here is the Salish Sea, Rosario Strait, Strait of Juan de Fuca. Down here, sort of between Olympia, Seattle, the Olympics and the Cascades, that's our Puget Sound. So in the Puget Sound, we have these land masses, and I'm zooming in really far. Give it a second to clear up. And what you'll note is on these land masses, we have these really straight parallel lines. You're like, wow, where did those come from? Oh, I wonder. So these straight parallel lines are so fucking cool. They're glacial, we call them glacial striations. And there are a couple things they could be, but what we know for sure is that they were carved out by the last glacial maximum. So you have this ice sheet that is moving like a river down a valley, through a valley. And in terms of ice sheets, like the Cordilleran ice sheet is so fucking massive that it covered the entirety of Puget Sound. Let me go back here. So here's the Puget Lobe. Covered all of the Puget Sound and went as far south as Olympia, Washington. So this was a massive ice sheet. Again, in Bellingham, it sat at about 2 miles thick during this maximum time. And imagine, so this ice sheet is moving from the north to the south very slowly, and it's huge, It's thick, it's dense, and as it moves down, it actually plucks, we call it plucking, rocks and boulders and gravel and sand, any kind of rock that it wants to grab, it's going to grab. And it scours out all of this material. And then all of a sudden it's sliding along this Puget Sound and it effectively acts like a giant fucking coarse grit sandpaper. So it carves out all of these rocks that are stuck in the glacier, are carving out the rest of that bedrock. And one thing, oh God, I don't know if I talked about it in this class. Let me go back here. Oops, wrong one. Let me go back to here. One thing to note is, oopsie, the material that make up most of the Puget Sound, like the geologic material, is very soft. It's sedimentary rock. A lot of it is unconsolidated, which means it's not actually a rock yet. It's just gravel or pebbles or sand. But a lot of the material through here is sandstone, conglomerate, shale, very soft material. And the rocks that were carving out this area were much harder. They were like granites, andesites, primarily granites, actually. All of this granite that we see in this area came from Canada. So imagine these rocks are scouring out this area. Oopsies. Ah, trying to zoom in here. And they scoured out these lineations, these lines that tell us a couple things. They tell us, A, what direction this glacier was moving. So you can see here they're moving north to south, but they kind of start to move east to west as they get further south, because this ice sheet is sort of spreading out as it gets further out. So cool. And I also want to make a point that we know that there had to have been rocks carving out this area for a couple reasons. But think about the fact that ice is, while it's heavy and it's dense, it's not hard. That ice is not going to do the actual carving itself. So the material that is doing the carving is other rocks that are stuck under this massive glacier that's just scouring out this whole area. And imagine you have this coarse grit sandpaper. You are putting all of your weight on this coarse grained sandpaper because that's how much fucking mass there was in this ice sheet. Okay. So my point, yes. Boop, 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 boop. Here are those striations. I just wanted to zoom out so you could see them. So I just went to Lopez Island last weekend. Oh God, I don't even know what day it is anymore. Last weekend, with I worked down at Skagit Valley College, and I went with the Environmental Conservation Club, and they were all excited about the plants and stuff. But I went down and I was like, "We're gonna go find some cool rocks," and they're like, "Yeah, let's do it." So we went down here. This is called Iceberg Point, and we hiked out to the point. And on this point, it's very famous for having these massive fucking glacial striations. So here I am, me for scale, on a boulder. So we call these glacial erratics. And what these are, and you can see one here too, is so the glacier carved out all this material, right? And when it receded, when it melted, all of those rocks that were once stuck at the bottom of this ice sheet just dropped. They just fell into place because again, this ice sheet is not moving. It's not physically moving backwards. It's just melting. So as it melts, all of this material just pops down into place and stays there. And we call them erratics because A, they don't come from here. This is definitely, these are granites that came from Canada. And they're massive. They're huge. Not all of them, but a lot of them are really big. So these guys are glacial erratics. You can see how this carved out this trough. I have some other really cool ones. I'm just really excited about it. It was one of the coolest trips I've ever been on. So this guy was really cool too, and I had to take a picture of this one because, so here's the erratic, and it carved this trough out, this basin. I do not understand, and I'd love to learn more. I need to go back and like dig out all this gravel and like really get a sense of this. I don't know how it has this like weird S shape to it. I don't know. It's really fascinating. I got it like oh, let's get under the trough. So here's the same thing. And what I notice here is that it's kind of coming up or going down. So I don't know if it like scoured deep. I don't know. I don't know how this happened, but it's really fucking fascinating. But this is a glacial striation. This is sandstone, by the way. It's very weathered sandstone. So you have this granite that's just scouring out all this sandstone. It's so fucking cool. And then here's another one that's really interesting. This glacial striation was actually along a wall. So it was not on a horizontal landscape. This was more vertical. So the ice sheet like molded its way into this little kind of valley. So this grass here was like a valley. I'm standing on one side of the bowl of the valley, I guess. So here's one end, and then there's a valley with grass, and then the other side. And so this glacier just scoured out on the side. There's actually four. We have one, two, three, and then four striations that were carved out um, because of this landform. So it was really fucking cool. That's it. That's my PowerPoint slide. So that's the cryosphere. It's not a, I say that. I've been talking for a long time, so we'll see how long this video was. It's a really fascinating part of our climate. And next week, when we talk climate change, we're going to dive into why all of this, how all of these come together, and why it's really important. Okay, let's stop sharing. Henry ran away, otherwise she would say bye. Okay. I'm going to do a video that talks about the lab and the homework here.